Here's our example. We have a region that is bounded by the curve y equals 2 square root of x, that's my function. The x-axis, that's the bottom. X equals 4, that's this vertical side. And we're going to revolve this region about, we're going to revolve it about the x-axis. All right? And while our task is to set up an integral that finds this volume, and we're going to do it two ways. One, use the shell method, and then number two, use the disk method. So, shell, first off, if we're using the shell method and we're revolving about the x-axis, the question is, which is the axis of partition? Well, shell method is the other axis. Shell method is the other axis. Revolve about x, so you partition y. So the question is, where does the partition start and where does it end? It starts at the bottom of the region, the original picture, and ends at the top of the original picture. Really, the only picture you need to work this out is the original region. So, the bottom is at 0, and we can show that if this is 4, 2 squared root 2 is 4. So we know the top of this is also 4. So we're partitioning the y-axis, which means the volume is given by an integral, and we know it must be dy. And we know the limits of integration. It's 0 to 4. Not this 0 to 4, it's this 0 to 4. And we're using the shell method, so we know the multiplier. The multiplier is 2 pi in the shell method. When we do the disk method pretty soon, the multiplier is only 1 times pi. All right? The next piece is we need the radius. That's rho. We need the radius. Well, if I take, this is the partition, so that tells us that these rectangles run this way because the partition determines the thickness. This is delta y, right? And so the question is, what is this radius? That radius is that y coordinate, right? When y equals 0.2, that's the radius. When y equals 0.3, that's the radius. When y equals 0.4, that's the radius. When y equals 3, that's the radius, right? So the radius is given by the y coordinate. Anytime you're revolving about the x-axis, if you revolve about the x-axis, the radius is the y coordinate. This is the radius rho, and that is the y coordinate. All right? Now we need the height. The height is how far is it from here to here? Well, if it's vertical, it's top minus bottom. If it's horizontal, it's right minus left. Right minus left. All right? Well, what is the right-hand distance? That distance we know, that distance is uniformly 4. We know what that distance is. That distance is the function value. All right? So it's the right minus left. So I'm going to rewrite this, give me some more space here. If it's right minus function value, watch. If here comes some wrong. I'm now going to do this wrong. Here comes wrong. Do you see why this is not correct? This is not correct, what I have written here. Yes, it is right minus left. It is this value, which is 4, minus this distance is the function value, but the function value needs to be, this means the function value of y. So we need to back solve this expression. If we're going to have dy, then this needs to be a function of y. In fact, as soon as you know the variable of the integral, then you might as well go back here and solve everything for y instead of x. And so what we may say is, in this case, this is not correct, but we do know that if we have y is equal to 2 square root of x, then we have y over 2 is equal to square root of x. So this is y squared. We can write this as y squared over 4. And that is the piece that needs to go here. So our volume is given by 2 pi, integral from 0 to 4, y, and then we have left-hand side, right-hand side minus left-hand side, which is expressed as a function of y. And we're out. If all you're asked to do, and typically on this section, in this chapter of material, all I'm going to ask you to do is set up the integral. all you're asked to do is set up the integral. As soon as you set the integral up, you're done. You don't need to try to simplify it. You don't need to try to evaluate it. That's the value we're looking for. So that's the shell method. All right. Now let's go back to the very start here. And let's work the disk method. Well, the disk method, we're revolving about the x-axis. I'll do this in red. The disk method I'll do here in red. The disk method, the axis of partition is the same as the axis of revolution. And the disk method, the volume is pi times the integral. And since we know we're partitioning the x-axis, this needs to be dx. And what I need is a function for the radius. All we need is the radius, because this piece, if we take this piece and rotate it, we create this disk, and we need that radius. Well, that radius is the function value, and this is a function of x, so we need the function value to be a function of x. So this is pi times the radius pi times the radius squared, and they enter limits of integration. On the x-axis, we're going from 0 to 4. It was a coincidence because I chose a kind of a smarmy little function that the limits on the x and the limits on the y are the same. That's a coincidence. But this is the disk method. Pi times the radius squared times the differential, as opposed to what we had before, which was the shell method.